All right, so today we're going to talk about Snell's law and really just more, doing an example of Snell's law. Um, so that way you get better practice, and if you're stuck, you can actually come look at this and hopefully answer your problem. So real quick, I'm just going to draw up here our refraction diagram. My goodness, that was a mouthful. Um, and so this is what they typically look like. And so we'll have right here is going to be that boundary of our medium. So we're going to have that. And then right here is going to be where we have our normal line. Oftentimes we'll call it a perpendicular, simply because it runs perpendicular to that boundary line. So that's where that comes from, because right here we get that right angle. Whenever you form a right angle with a surface like this, we call it a normal. And that's something that's in general across in physics. So with these, we're going to have a light coming in from this direction, or from some direction, really anywhere on the top, and coming from any angle. It could be coming from this direction, or it could be coming from this direction. And then it's going to enter in this new medium, which I have not identified what any of these are yet, and it's going to bend that light in some way. Now, before we even jump into that, just kind of a general thing. Now, if we have a light coming in from this direction, if it bends closer to the normal, that means that the index refraction on this side is greater, and therefore it's slowing down that wave more. If it's less than what's on this side, it's going to bend up and bend more towards the actual surface, that boundary, or away from the normal. And what that means is that the index of refraction of this medium A is going to be smaller, or greater, sorry, than the medium B, which will be greater. So a lot of times, based off that refraction, depending on the angle it increases or decreases, you can already tell what type of answer you should get if you're trying to find n, which oftentimes you will, and a good way to kind of self-check your answer if it makes sense. So let's go ahead and let's say, so we have our light coming in on this direction, and so our light's coming in there. And now it's going to get refracted because it's entering that medium. And so now let's say that it's going, let's do an example, because we've done a lot where we go from air into water or glass. Let's do, it's going to bend up this way. And so now, as you may have figured out, is what I just said, this means that when this is going in, our index refraction up here must be greater than that's coming down here. So let's say that this is going to be glass, and then let's say this is air. All right, so now let's say that that's what we have going on. Now, we need to obviously have some things given to us, because right now we don't have nearly enough information to actually solve for, and I haven't told you what you're going to solve for yet. Now, we already know, and this is kind of a constant, let's say air's index of refraction is going to be 1, and then let's say glass, well, let's say we're trying to figure out what that is. Maybe we don't know what this glass is, we want to know, but we have a light going through it, and we see what our light's doing after it, so we want to know what our glass is. But we do know this angle up here, and so let's say, and this is going to be our theta I, and let's say that that's going to be, let's call that a 45-degree angle. That's a pretty big angle. And now on here, now this is, we're doing our angle from the normal, right? So make sure we're not doing it from this point up over here, because then you're going to get a wrong answer. We're always doing our angle from that normal, because that's truly what we're measuring. That's our reference point. That's why we put it in there, because we know that way what it is. So that means that our angle here, let's call, that's pretty big. That's definitely bigger than a 45-degree angle. Let's do, let's call it, let's say move to 65. So a pretty big difference degrees. So now we have everything that we need to have for our Snell's law. So remember, Snell / equation is going to tell us that our Ni times our theta, excuse me, I'm getting ahead of myself here. There we go. I'm sorry about that. All right, that our theta I multiplied by our, oh goodness me, got off my pen. All right, there we go. Our sine theta I is equal to our n index of refraction r times our sine in that same, or not same, that angle r. So that's going to be here, and so I should put that label on there. Theta r. So now we have all this information, right? So we have our theta I, we have that incident angle, we have our refracted angle. We do not know our Ni, that's what we're trying to figure out. So that's our glass, but we do know our Nr, and that's going to be our air. So let's go ahead and plug all those things in. So we're going to have our Ni is going to be equal, or not equal to, my goodness, I'm just jumping ahead of myself here. Ni is going to be times, our sine of 45, which is then going to be equal to our Nr, which we said was 1 times our sine of 65. And so now what we need to do is then we really need to solve for our Ni. So we can simply just divide over our sine 45, and then what we'll get is our Ni, and this is what I actually jumped to beforehand. I got excited, I got ahead of myself. Don't do that, that's how mistakes happen. We got then our sine 65. We're going to divide by our sine 45. And that's going to get our answer. And so here, give me a second, I'll just punch those in quick. And now we get, if we punch that into our calculator, we get, and at least what I get is 1.28, and then there's a bunch of decimals after that, but we're just going to leave it at 1.28, that's what it'd round to. And so that's going to be equal to our Ni, or really that's going to be glass. So then our glass, that we have our mystery glass, is going to have an index of refraction of 1.28. This is actually pretty low for glass, because typical glass, and if you look up on a chart, is going to be about 1.5. But you know, it's possible that a glass would have this sort of index of refraction. So it's going to be 1.28. That's what we proved mathematically with all this over here. So yeah, I generally like finding the index of refractions. They are a little bit easier. Otherwise you get arc sines, and we'll have a separate video of how we're going to be doing that. So if you have any questions, please do let me know in class.